Okay, I think we can start. Hello, everybody, and thank you for joining us today, and welcome to the ASTRO 3D ECR Astronomers in Australia seminar series. My name is Dorota Bayer, and I am an ASTRO 3D postdoc at the Swinburne University of Technology in Melbourne. My co-chair today is Dr. Meredith Joyce from the Australian National University in Canberra. Before we begin, we must acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I am speaking to you today from the land of the Wurundjeri people of the Kulin Nation, and my co-chair Meredith is joining us from the land of the Ngunnawal people. Our first speaker, Sabine Belstedt, is speaking to you from the land of the Whadjuk Noongar people. And our second speaker, Piyush Sharda, is speaking from the land of the Ngunnawal people. We pay our respect to the elders, past and present, and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by ASTRO 3D, the Australian Research Council Centre of Excellence for all sky astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year. Especially for us in Australia, the time zones mean that often meetings take place at 2 or 3 in the morning. And this lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world.
So next up we have Piyush Sharda. So Piyush, you're welcome to share screen.
Awesome. Hi, everybody. Thank you all for joining. I'm Piyush. I'm a PhD student at the ANU in Canberra. And today I'll be talking to you a bit about some of the work that we have been doing here in terms of modeling the metallicity gradients in galaxies. So just taking a step further from what Sabina has been talking about, but really looking at individual galaxies in great detail and figuring out how is the spatial distribution of these metallicities in these galaxies is like, and can we really understand something about galaxy evolution itself from the metal distribution of galaxies, and how do we do it, or how can we model it? This work has been done in a collaboration with a lot of people, in particular Mark Krumholz and Emily Wisniewski, also at the ANU. Just to set the scene for this talk, I'm only going to talk about gas phase metallicities, meaning oxygen abundances. So whenever I'm referring to metallicities in this talk, it only means oxygen in this context. It's been possible in the last decade, more or less, where we have now really started to look at the spatial distribution of metallicities in the galaxies. We have had this, measurements of global or integrated metallicities of galaxies since the 80s or the 90s, but through the advancement of recent IFU surveys, we can now look at individual H2 regions in galaxies, measure their metallicities, and sort of get a metallicity map out. I'm just showing here the metallicity map of NGC 2997. It's a local spiral galaxy around 10 megaparsecs away. And you can really nicely see how the metallicities are really, really high in the centers. And as you go in the outskirts, the metallicities drop down. To get a metallicity gradient out of this, it's a 1D measurement. You just go along any particular azimuthal direction and just measure the metallicity along that direction as a function of radius, which is shown in the adjacent plot here. So you sort of get metallicities as a function of the radial distance in the galaxy. And all you do is you sort of fit a linear curve to it, and the slope of that curve tells you what the metallicity gradient is like. Now, typically, in the context of inside-out galaxy formation, which is how we think most galaxies formed, we get a negative metallicity gradient because the centers are more metal enriched and the outskirts are metal poor, just like the galaxies shown here. So there have been a lot of observations like these that have piled up in the last decade. And simulations are now also starting to catch up with these observations. So here is just an example simulated galaxy from Illustris TNG by Hemler et al. where you also sort of see a very, very similar spiral pattern that is tracing metallicity, which is tracing the spiral pattern, and a similar sort of a negative gradient in metallicity in the gas. With all of these observations as well as simulations, we are now really starting to make progress in terms of understanding the physics of metallicity gradients, which is where our model sort of fits in as well. So in our model, what our model contains is nicely summarized in this plot, the so-called bathtub model by Simon Lee, where you have inflow of gas into the galaxy. That inflow sort of triggers star formation, which sort of produces metals. Metals are advecting into the galaxy, which means they are moving with the bulk flow of the gas. Metals are also getting diffused in the galaxy because of concentration gradients. Metals are also consumed by stars, which whenever they explode, whenever they die, they will return those metals back into the ISM. And throughout this process, metals are also being lost through galactic winds. This sort of a picture really, really summarizes the entire metal budget of a galaxy. And you can see there are certain processes that impact this budget, which are like sort of outside the galactic disk. There are a lot of other processes which happen within the galactic disk itself. So to understand the spatial distribution of metallicities, we really need to look at the entire galaxy as a whole, as well as on very, very small scales. So the model that we have, or that we have developed, includes all major modes of metal transport. And by transport, I mean all the different ways in which metals can move around in a galaxy through accretion or outflows or advection or diffusion. I'll keep using the words advection and diffusion a lot because so far the current literature has sort of not really covered metal diffusion or metal advection when they talk about metallicity distribution in galaxies. The model can be applied to a wide range of galaxies, both in the local and the high-redshift universe. And I'll show one result or one application of the model from the local as well as the high-redshift universe. And most importantly, in the work that we have carried out so far, we are not fitting any data to get the model parameters. So it's just plainly pasting the model on top of the data to see how it looks like without fitting the data to get anything out. We do not really like equations in slides and presentations, but this is a very important equation for me to talk about, and I'll go through it point by point. This equation sort of summarizes everything that metals are doing in a galaxy. And if you can solve this equation, you sort of have a handle on the metallicity gradient of a galaxy. This term on the left here talks about the equilibrium of metallicity. So after a certain amount of time, the distribution of metals in a galaxy will reach equilibrium. And this term says, when does that happen? This term here talks about metals being advected in the galaxy. So how metals are moving with the gas. So wherever gas is moving, it is taking metals with them. This term here in particular talks about diffusion of metals. So obviously gas does not diffuse, but the concentration of metals within the gas will diffuse. And it's important to take this term into account as well when you're talking about the distribution of metallicities. This term deals with metal production, basically star formation. This term deals with accretion of gas onto the galaxy, where we have a lot of, where galaxies are always continuously accreting metal poor gas from the cosmic web. And that gas is ultimately responsible for triggering star formation. And that has a lot of impact on the entire metal budget of a galaxy. And the last term here deals with metal outflows. So how many metals are carried out through galactic winds? In subsequent applications of the model, we'll see that outflows are really, really important for us to be able to talk about metallicity gradients. We really need a good handle on what are outflows doing and how many metals are outflows carrying in different galaxies. And once you solve this equation, you sort of get a very, very simple analytical result, where you can just express metallicity as a function of the radius in the galaxy. And once you can do that, you just do what the observations do, where you just fit this with a linear curve, figure out a metallicity gradient from the model. Now, you will notice that I've highlighted some parameters in this equation in orange, and I call them T, P, S, A, and phi y. So these are the 5 things that really basically that vary from galaxy to galaxy, and that sort of provide how metallicity distributions are like in different galaxies. But to summarize, here is how we can understand the trends that we will see. If S, which is related to metal production, if this is stronger as compared to advection or accretion, we will always get very steep negative metallicity gradients in galaxies. If P or A, by which I mean advection or accretion, are more than S, you will always get shallower metallicity gradients. So essentially what is happening is star formation always wants to create a very steep negative gradient. And that gradient or the steepness of that gradient is then balanced by advection of gas, diffusion of gas, or accretion of gas. And we will see for different galaxies in different regimes in the local and the high redshift universe, different terms become important and they dominate the overall spatial metallicity distribution of galaxies. So let's talk about a couple applications in the time that we have left. The first one that I will talk about today is the local mass metallicity gradient relation, or as I call it, the MZGR. So it's sort of a funny turnover of the word MZR, which is the local but global mass metallicity relation, which has obviously been very, very well known since in the last 20 years or so. But recent works based on IFU galaxy surveys in the local universe, like SAMI or Khalifa or Manga, have also been able to produce a mass metallicity gradient relation where they plot the metallicity gradients as a function of galaxy mass for like several hundreds of galaxies for which they have the resolution to do this analysis. It's a very, very recent relation. It's a very, very recent finding, and we still do not really understand how is an MZGR developed. And there has not been much research that has been done in this topic in particular. So let's take a look at what the model sort of gives you when you want an MZGR or a mass metallicity gradient relation. So I show that in this plot here, where on the y-axis, you have the metallicity gradient in units of Dex over RE. You can ask me about the units later, but that's one of the common units we use to measure metallicity gradients. And the x-axis here is the stellar mass. Now, you see that there's a bunch of transition in the color bars. That color bar denotes the ratio P over A, which means advection over accretion. The length of this color bar tells you about the outflow metallicities in galaxies. So if you are at the bottom of this color bar all throughout, that means that the wind metallicity is very similar to the ISM metallicity, which means metals are very well mixed in the ISM of the galaxy before they are ejected. If you're up the top here, it means the wind metallicities are very, very high as compared to the ISM metallicity. So this is corresponding to a scenario where as soon as you produce your metals, most of them are directly lost through galactic winds because of like lower potential wells or lower disk scale heights and so on. So for some galaxies, we expect the wind metallicities to be really high as compared to the ISM. For some other galaxies, we expect the wind metallicities to be the same as the ISM. Theoretically, the wind metallicities can never be below the ISM because that will sort of violate the metal budget conservation. So if you are in this red space, the value of P is more than A, which means advection dominates. So advection is the one that will try and make the gradients shallow or flat. If you're in the blue range over here, accretion of gas onto the galaxy dominates. So it means it's gas accretion onto the galaxy that will dominate and give you flatter gradients. And there is a transition regime in the middle where galaxies sort of transition from this advection-dominated regime to an accretion-dominated regime in the model. Now, let's try and put some of the known MZGRs from the data that we have onto this plot. And this is how they all lie. So all the orange points here, there are 3 different sets of orange points. They are from the 3 different IFU surveys that have been carried out in the local universe, Manga, Khalifa, and Sami. And the gray points is basically an average of all the 3 different surveys taken all together. This is data from Ayan Acharya's paper, which is in prep at the moment. But this data is also publicly available. So what do we see? At the low mass end, we see that galaxies tend to lie closer to this side of the outflow metallicities, which means at the low mass end, outflow metallicities should be higher than the ISM metallicities, which means low mass galaxies are preferentially ejecting a lot more metals. At the high mass end, the galaxies tend to lie towards the bottom of this color bar, of these colored bands here. So in these high mass galaxies, the wind metallicities are very similar to the ISM metallicities. And there is sort of a transition regime in here, which is still debated, like it depends on who you ask. Some people do see an inflection in the MZGR in the data. Some people do not, and it's still a matter of debate. But what we learn from a comparison between the model and the data here is that firstly, we see a transition from an advection-dominated regime to an accretion-dominated regime. And this transition sort of corresponds to the location where the MZGR shows a curvature, as well as low mass galaxies, so less than 10 to the power minus 9, 10 to the power 9.5 solar masses galaxies. They preferentially lose metals in galactic winds, which immediately tells you that galactic winds are really important to understand what is driving the MZGR. And there have been very, very few observations that have actually looked at this observationally. So we need more observations where we can measure the metallicities of galactic winds, really. I'll talk about the second application in the time that I have remaining, which is an application of the model at higher redshifts. And when I say high
5 minutes.
Thank you. When I say high redshifts, I mean between redshifts 0.5 to 2.5. So for some of you, it might be high, some of you might be low. I'll leave that up to your interpretation. So we have looked at how metallicity gradients vary as a function of stellar mass, if there is a variation at all. But we can also test with this model whether metallicity gradients show any trends with the kinematics of the gas. And when I say kinematics, I mean things like the velocity dispersion of the gas or the rotational velocity of the gas. Now, testing for gas kinematics is more easily done at higher redshifts. And the reason for that is summarized in this plot by Emily Wisniewski and collaborators. You can see that at redshift 0, most star-forming galaxies have a very narrow range of velocity dispersion. So there is not really much to test. It's a factor of 2 deviation at most. But if you go to higher redshifts, you have this entire big diverse range of velocity dispersions that galaxies show, which means there is a much broader range over which you can test any model like this to look for any correlations or trends. And again, like the local MZGR, the role of gas kinematics in setting these metallicity gradients is again very poorly understood. And to the best of my knowledge, there are only 2 results out there that have even put metallicity gradients with kinematics on the same plot and have talked about it a bit. Again, so let's start with the model first, remembering that we are not still fitting the model here to the data at all. The y-axis here is metallicity gradient, now in the units of dex over kpc. So I've just changed my units here and just to match with the observations better. The x-axis here is the gas velocity dispersion. And the 3 different model curves that you see are for 3 different values of the rotational velocity. So what you do is you fix the rotational velocity in the model, and then you just vary the velocity dispersion, get a metallicity profile, fit the metallicity profile, get a gradient out. And that's how you get this curve. Now, a special thing about these curves is that they're only for the case where the outflow metallicities are the same as the ISM metallicities. So what this means is that these curves are only showing the steepest or the most negative metallicity gradients the model can produce for a given rotational velocity. This is sort of a different way of looking at the data, and you will see why in a moment. But these lines are simply providing some lower bounds on the value or the strength of the metallicity gradient that galaxies can have in this redshift range. And if you plot whatever data is available after homogenizing the data, because the data comes from different instruments and different techniques and stuff like that, again, you see the same P over A and P less than A and P greater than A transitions. So basically at higher velocity dispersions, you have a lot of advection, because advection goes directly with velocity dispersion, which means you're mixing metals very quickly, which is giving rise to a very flat gradient. At lower velocity dispersions, the relative strength of advection is very weak, so you cannot mix the metals very well, but accretion really becomes important. And accretion creates metal dilution because you're accreting a lot of metal poor gas from the cosmic web. So it again shallows or gives you flatter gradients by giving you a shallow distribution of metallicity across the galactic disk. And there is a transition in between. Again, you will see that this transition between the P less than A to P greater than A regimes, we sort of see this in a lot of different applications of the model in different contexts. And this is how the data is like. So what I've done here is I've simply binned data, which is spatially resolved measurements of metallicity gradients and velocity dispersions in around 75 galaxies between these redshifts taken from different surveys. I've binned the data in different bins of V5. And you see that the bounds that the model produced sort of nicely align with the data that is available in hand. And again, this is not a fit. It is just almost too surprising that this looks like it's a fit, but it's really not. Which means that at higher velocity dispersions, what we learned from this model data comparison is that you have efficient metal mixing, which gives rise to flatter gradients. So this is what I would call a flat gradient. At low velocity dispersions in this regime, you have efficient metal dilution, which again gives rise to flatter gradients. And at intermediate regimes where both metal dilution and metal mixing are weak, star formation can win over, and it can give you some steep gradients and a larger scatter. Now, one of the possible reasons for a larger scatter at intermediate velocity dispersions in the data could be due to different outflow metallicities again. And this is something that is yet to be tested. So to summarize, we have developed a new model to understand the physics of gas phase metallicity gradients in galaxies, both in the local and the high-redshift universe. I have only covered two particular results or model applications in this talk, namely the MZGR, where we see a transition from accretion to advection-dominated stages, as well as some dependence of, or some trends of how the outflow metallicities should scale with galaxy mass, where low mass galaxies show more enriched outflows. And we also have studied a particular trend with the gas kinematics and what the role of gas kinematics is in setting metallicity gradients. There are some other results and applications that I've not covered in this talk. And all of the details regarding these applications and the model are in a series of paper that we just put on archive a couple of months ago. So please feel free to go and check them. I'll stop here and I'm happy to take any questions. Thank you for your attention.
Okay, thank you, Piyush, for a really excellent talk. We do have a few hands up. So one is Gerhardt, which may be left over from the last hand raise, but we also have, okay, that's down now. We have Sabina, so please go ahead.
Probably a naive question from me. Is your model able to say anything about whether, if at all, that transition mass from the advection-dominated zone to the accretion-dominated zone, whether that mass changes with redshift at all?
That's a very good question. We actually haven't tested this at different redshifts because I don't think that there was any data basically to compare this with. But with the model, you can definitely sort of make the same plot at different redshifts and see how that transition mass changes. That's a very interesting point, which could be done without the observations as well, just to have a look, but I haven't done that yet.
Okay, yeah, we have hands up from Eric Lang and Luca Cortese. So I guess Eric first.
Okay, thank you. Thank you for the nice talk. I was wondering if you have looked at mergers. For example, what do we expect mergers to affect their metallicity gradient, etc., etc.? Is it also reflected on your relations? And also, I was wondering if you have looked at the environment of galaxies. For example, if they are central galaxies or satellite galaxies, and what's the effect of this? Thank you.
Thanks, Eric. These are two very nice questions. So in fact, we have looked at merging galaxies. In particular, we have looked at major mergers in the local universe. And what we find is that this model may or may not apply to those galaxies, because we show in the first paper that in merging galaxies, the distribution of metallicity may not reach equilibrium within the duration of the merger itself, which means an analytical approach like this, a steady state approach like this sort of breaks down. The approach also breaks down if you have inverted gradients in some cases. In some cases, you can get an inversion of the gradient and still be in equilibrium. In some cases, you cannot. So yeah, merging galaxies, I would say, largely are a case of a non-equilibrium distribution of metallicities. With regards to your second questions on the galaxy environment, we haven't looked at that through this model. And the main reason for that is this model talks about the metallicities, but it needs input from a galaxy evolution model. And we are using Mark Drumholz's 2018 Unified Disk Galaxy model here. So if I quickly go back to my equations here, sorry, all the parameters that you see in these equations, T, P, S, A, and phi, Y, you can express them in terms of galaxy parameters, which needs to come from a galaxy evolution model. So this model takes as an input a galaxy evolution model and outputs the metallicity, which ensures that the gas is being treated self-consistently with the metals. So if there is a galaxy evolution model out there that has the effects of environment in it, you can crunch it through this metallicity model, and then it should be able to predict something for the metallicities as well.
Okay, I see. Yeah, that's very clear. Thank you.
Thank you.
Okay, and just barely have time for one more question from Luca. Please go ahead.
Thank you very much. This is super interesting. I have a question about application number 1. So regardless of the data, your model seems to suggest a wide range of potential gradients up to 10 to the 10.5, but in solar masses. But then above 10 to the 10.5, you predict a very, very narrow range of gradients. What's the physical reason for that?
Right. So it's a very interesting question, Luca. Thank you for raising this. You can see, irrespective of the data, yes, the range in blue is very narrow as you go to very massive galaxies. And the length of these colored bands that you see on the slide, they are decided by the metallicity of the outflows. So what is happening at very, very massive, at the end of the very massive galaxies, is that regardless of how many metals your outflows are carrying, the gradient that you expect will always be flat, because these massive galaxies can accrete a lot of gas. So the dilution of metals is really, really strong, and it always wins over. So if I could quickly show an extra slide that I had, yep, which is basically the metallicity gradient on the y-axis and the total metallicity of the galaxy on the x-axis. And the different curves represents different outflow metallicities, simply speaking. If you look at the highest mass, the most massive galaxies, they are all of them show gradients between 0 and minus 0.02 dex per kpc in the model, regardless of the outflow metallicities. And the main reason is metal dilution.
Perfect. Thank you very much.
Thank you.
All right, it's time to wrap up. Thank you very much, Sabine and Piyush, for your exciting talks. And thank you everybody in the audience for listening and attending.